so without further ado, I'm going to get started. So regarding my job title, Manager of Demand, since that question is fresh in my mind, basically I forecast demand, and that will become quite apparent as we go through the slide deck. Okay, so before we begin, I always like to give credit where credit is due. And in that case, Dr. Rob Hinman has a fantastic book. It's very readable, very user-friendly, that has helped me out a lot. It's called Forecasting Principles and Practice. And note the third edition. There are other earlier editions which are based on his old package, Forecast, which is was a good package, but the Tidy Verts is just as head and shoulders above that. So if you just Google Forecasting Principles and Practice, actually I'll show you a couple of graphics as we go through the presentation from his book, which are really useful. You can see the link. Also, you can, if you're interested in learning more about these topics after the presentation, our package FPP3 goes along with the book, and it will include relevant data sets. The cool thing about that package is that those data sets are really great for illustrating some of the concepts that are relevant to time series. So you'll notice when we look at my data, it's going to be real life data from my company, that it's not quite as clean cut. And then also definitely check out his website, blog. He has papers he's published along with various collaborators who are kind of leaders in the field, and then just blog posts, other good resources. Okay, so let's get into some definitions. What is a time series? You probably have some intuition about this, but let's be clear about what exactly a time series is. It is data that is measured over a period of time, usually at regular intervals, like month, quarter, or year. Sometimes there can be irregular intervals. It's a lot less common, and we're not going to touch on that today. It's a little bit more of an advanced topic. Okay, so there's a lot of uses that we can think of for time series if we analyze data, but the main use of time series is forecasting. So we have a data set, and then we want to predict what's going to happen in the future based on historical data. So a lot of times that's going to be, we're going to estimate a model and the parameters. And then we are going to use that model to forecast future values. So it makes sense, right? Pretty intuitive. So something to keep in mind is that the further into the future the forecast is for a given time period, the more uncertainty there's going to be associated with that forecast, since the previous values that you use to forecast are actually forecasts themselves. So if you're forecasting 10 months out and you have a model that has a lag 1, that 9-month out period, of course, would be a forecast. So there's uncertainty associated with that. And that is a predictor in that model. Okay. So types and uses. Obviously, we have a lot of different industry and government situations where we would think of forecasting. We also have different time horizons that we would consider forecasts for. Short-term forecasts, and I'm going to speak to this from a demand forecasting perspective, because that is my background. So the examples I give will be mostly tailored to that. So a short-term forecast might be production scheduling, customer demand, that's my job, in the next several months or years, but generally a short-term horizon. Medium-term may be used if you wanted to procure raw materials. So that's going to be looking a little bit further out. And then a long-term forecast might be used in a supply chain context for capacity planning. For example, if you're going to forecast long range, you might forecast at a high level, but you want to decide, is this a profitable decision to increase capacity at a plant given our long-term forecast? Okay, so the typical process flow. This is by no means a, you must follow this process, but I think this is a very helpful framework when you're approaching a problem, and especially any kind of modeling problem, but time series for sure. So first, Step one, define the problem. It may seem like of course, kind of a step, but you want to make sure that you're forecasting what your supervisor or whoever else, the customer of your forecast, wants to be forecast. Sometimes you might need to be cognizant of a data transformation, anything that's just something that comes to my mind, anything like that, right? So step two, collect info. That is going to be your time series data, of course, and then also organizational expertise. So you want to do your homework before you just start, estimating models. And that would be talking to people with expertise about the data, maybe in your organization, maybe outside. If you're building a model with explanatory variables that are not lagged values, which we will not be exploring that today, but there are a number of time series models that do have that. You might want to understand what are factors that are correlated with this time series data. Also understanding structural changes in the data. So perhaps the way something was measured changed at a certain time period, and you don't want to use any data that you might have available before that time period. Or maybe there's something you could do to mitigate that effect. So then step three is going to be exploratory analysis and data visualization. So you got your data, you have an idea of a model that you're interested in, and this is going to be plotting the data, always a good step, right? Any kind of data analysis, data science flow. And then you might do some summary statistics, other statistical tests, that kind of a thing. It will depend, of course, based on how much time you have, how large your data set is, that kind of thing. Finally, model choice and estimation. So you're going to estimate a model or several models until you get a model that you think, based on various statistics and other measures, is a decent first model. And then you will forecast. You'll evaluate those forecasts, which we'll talk about today. And then you might go back to the drawing board, maybe back to step three, see if you missed something in your initial analysis, or step four, maybe try a different model, different parameters, different structure. Or you might get lucky and have a great model the first time. Everybody wants that outcome. Okay, so how to think of a forecast. I should say this is a point forecast. So it is generally the mean of the distribution. It is a random variable that we are forecasting. It could take a range of values. So a lot of times a point forecast will be reported with a 95% prediction interval. So that if you're familiar with basic statistics, that gives the range of values for which there's a 95% confidence level that the actual value will be included. Now, just from personal experience, I want to add this caveat. You need to use good judgment interpreting the confidence interval. So in my case, I'll see confidence intervals which include negative numbers. Obviously, that is not feasible we're not going to have negative future sales, right? Now, in the companies that I have worked for, which include consumer packaged goods and pharmaceuticals, there's not a whole lot of attention that is paid to confidence intervals. It's more that point forecast that everybody's interested in. But depending on the context or perhaps the sophistication of your companies or organizations, forecasting system or methodology, that might be different. Okay, so the data. The data we're going to examine today, as I alluded to earlier, is real data from my company. So this is demand history. Demand history, as we define it, includes sales shipments to our customers. It also includes any open orders that we have not been able to fill, but they're still on the books. And then it could include future open orders. So we have both past due open orders and future open orders. And you will see, if you look at the data, it's a pretty small Excel spreadsheet. There are 4 SKUs. 3 of the SKUs are acetaminophen products. Those are my products that I forecast. And these acetaminophen, as you're probably aware, is what is in Tylenol. So that kind of gives you an idea of the kind of demand we're dealing with and the factors that would affect it. And then the 06Q, if you looked at the Excel spreadsheet already, is an ADHD product. And that is a dosage product, which in pharma lingo is basically, that is something that the consumer, is prescribed. The acetaminophen products are ingredients products. So that's a little bit different kind of a market. So the ADHD product is actually my coworker's product that he forecasts. I asked him for some referrals for products that had good illustrations of seasonality. And he likes to do his forecasting by dividing up the time series into groups based on customer demand. So we have different customer groups, and you will see that shortly when we take a look at the data.
I ask a quick question?
Sure.
You described the acetaminophen product. I'm sorry, you described the ADHD product as being a dosage product. And then what was the term you used to describe the acetaminophen product?
So we call it API. Now, it's not API like you think about it in a computer science or data science context. Active pharmaceutical ingredients. So this would be, in addition to making dosage products, we also sell we sell to our competitors in some cases, and they make, using our ingredients, they make dosage products. We would sell acetaminophen to certain companies that you were probably well aware of, which I will not comment on the names, and then they make dosage acetaminophen products. So
thank you.
Yeah, sure thing. Okay, so time series patterns. So we want to know a few things to look for as we look at our data. And the first thing is, a lot of these are probably going to be intuitive to you, but it's a good idea to make sure we define our terms. So trend is basically a long-term increase or decrease in data, may or may not be linear. Seasonality is changes in data that occur at fixed frequencies. So fixed frequencies being the key word there, time of year, day of week, that kind of thing. A cycle is basically a data increase and decrease that is not a fixed frequency. For example, a business cycle. So you might have a time series with all or none of these patterns. So for example, like a white noise time series would not have any of these, right? The data we're going to look at today is going to include series with trend and seasonality based on my judgment. And there is some judgment that goes into this. Forecasting is an art and a science, as a lot of practitioners like to say, but we're not going to see any cyclic patterns. And a lot of that is because of the nature of the data. I don't have a particularly long time series. We have about, and as well as it's not reasonable to assume that business cycles are going to necessarily affect pharmaceutical demand. Now, if we're talking about like T-bill yields, something like that, an economics time series, that would be different. Also, I will say about cycles, it's often hard to pick out a cycle until after it's over. For example, like a recession, expansion, that kind of thing. So just be aware of that if you are working with economic time series. Okay, so Janine alluded to all the, or mentioned all the packages that you will need to install. Dr. Heyman and his collaborators call these packages the tidyverse. Obviously, it's a kind of a play off of tidyverse. However, as of early 2021, you can't, unfortunately, load each package just by running install.packages tidyverse. So Tsibble, feast, and fable. And yes, it is pronounced Tsibble. Dr. Wong, who I believe is the main creator of Tsibble, she has said it's pronounced like cats. So I did look up the pronunciation to make sure I didn't butcher it. Okay, the tidyverse, though, what's really cool about these packages is that that they work with the tidyverse. And it makes it a lot easier to manipulate data and do other kinds of data analysis, as you're going to see. Okay, so Tsibble is our first package we're going to use. And Tsibble is the package that we use to turn the data into a usable form for time series forecasting. So as you probably guessed, Tsibble denotes a Tibble structure, so tidy data. Hopefully you're familiar with the concept of what tidy data is. Also, data frame, that kind of thing, with the time series aspect added. So Tsibbles often behave a lot like Tibbles. There's a few exceptions that we will go through later on in the presentation. Okay, so let's take a look at some code. I have the here, Janine alerted me to this, which I appreciated. She's the second person who told me I need to start using the here package. So I think that's a sign if there is one. But you want to make sure that the Excel file, ourladies.demandhistory.xlsx, is in the same folder as the .rmd file. Okay, and for me, that was just my documents file, my working directory. I'm not quite as organized with my folders as I probably should be, and I guess it makes it a little simpler for me in this case. So here's where our read Excel comes in. The only time you're going to use it all night, just read Excel. And so you're going to read in the demand history. And then you see that we convert our month column. The RS, if you're wondering, these were named by the IT guy I work with, who's been working on this forecasting project with me. And so he has RS for RStudio. So that's why it's named that. No special reason. And we convert this to year month, because if not, it'll just be a character based on how the data is stored in my company's database. So I'm going to head over really quick to, I want to just kind of show you guys what this looks like. It's easier when you can kind of scroll through it. So you see that we have several columns. I'm going to move this over so we can see that. So we've got, this is a business unit. This is for our generics business unit. And then this is our family. We divide our data into families and then subfamilies. And then this is an abbreviation. I can't remember off the top of my head what it is. This is our item. And then this is demand group. So we have, you'll see if we kind of scroll through. And we, if this data set wasn't so small, it's only 248 rows, you'd probably be better off doing some, summary and other kinds of tidyverse or perhaps space R functions to analyze it, but we can kind of scroll through it because it's pretty small. So we see that we have this now. Here's something kind of weird, right? We've got January 2018 after, I think it was June 2018, right? That's kind of weird. Not cause for concern yet, because we haven't converted it to a Tsibble. That'll take care of it. So we just kind of scroll through. Sometimes it's a good idea to take a look, just make sure everything looks good. And then we see we have demand going. As I mentioned, demand includes our open orders in the future. So we have some customers who are nice enough to place orders far in advance. I pulled this data in February 2021. So the last month for which we have complete data is January. So we're not going to be as interested in these future months, just given that it's not complete demand at this point. Okay, back to the presentation. And the good news is, looks like all the type of each column is as we would expect. We've got a double type for the quantity over here. So that's all good. Okay, so attributes of a Tsibble. So we have a data frame or a Tibble. We need to specify an index and key if necessary. Keys are not always necessary. You could just have a quantity variable or several quantity variables and an index variable. But a lot of times if you have a data frame, you're going to have a key or more than one key. So in our Tsibble, the RSF month column is the index. the time variable, and the other columns except the RSF quantity are the keys. So the keys indicate how many models / forecasts we need to estimate and then calculate. We calculate forecast, we estimate a model. So for example, we had a Tsibble with 2 keys, one of which had 3 unique items, and each of those 3 items in the first key had 3 items in the second key. We would have 9 models. It's kind of some, permutation math there, so to speak. So in this case, we have 4 SKUs, 3 of which, those are my SKUs, that, well, I guess it's all my SKU, but my SKUs, but the ones that I am responsible for have 1 customer demand group, and that's just our global demand. And then one of which, my coworker's SKU, has 5 customer demand groups. So we're gonna have 8 models if we forecast at the lowest level. Just a little caveat here. If you're doing hierarchical forecasting, which we won't be covering in this presentation, but if you take a look at the forecasting principles and practice book, you'll see a chapter on that. This math does not apply, so that's going to change how many models you're going to get. Okay, so converting to a Tsibble. We have a very handy, easy function as Tsibble, and then we just pass it our data frame. Similar to the tidyverse, we don't even need to quote the columns that are our keys, and then we index, we pass it the index. You can take a look. You see it's still 248 rows. That's good. That's what we'd expect. We see that the types of the columns are all the same. And now, if you notice, everything is in order, right? Before we had had different. It was a little bit out of order. Notice also that it has been alphabetized, which is kind of fun, I guess, but not necessarily necessary. So there is another function. Most of the time when you're working with Tsibbles, you'll have a data frame that you import either from a database or Excel, CSV. But if you just want to create a small little Tsibble yourself, there's just the Tsibble function, and you can add columns, specify key and index. So if you're playing around with these packages and you want to try that, I'd encourage you to do that. Okay, so as I alluded to earlier, the data there's more data than we want here. So there's a longer time span and that we want to use for this analysis. So we're going to use the filter index function. So as you would guess by the name, we can filter the index based on a start date and or an end date. So as of early 2021, and I say this because I believe that some of the syntax might have changed in the few months since I started using this. I guess it was about these packages about 8 months ago or so, 9 months. The start and end dates must be passed as character strings. Okay, so let's see this in action. We've got filter index, and we literally just put this in a character string. We got our tilde, and then we have to January 2021. So this is inclusive on both sides. And you can see we went down a little bit to 27 instead of 248. We have all of our same columns. And also, I'm assuming that most of you, if not all of you, are familiar with the pipe operator, but just want to call that to your attention that you can use that in the same way as you will with tidyverse verbs, and that is a really nice feature. It makes your workflow a lot easier for these packages. Okay, so this is not necessarily pertinent to what we're going to be doing today, but I wanted to let you know another way you can use filter index. So if you just want to get a year, basically the point of this is you can be really lazy with some of these packages. So I guess that's nice if you're trying to do a lot of coding. So let's say I just wanted 2020 data for some reason. So I can, for whatever reason, it doesn't work for year month type. As of when I created this slide deck a few months ago. So I convert this to as date, and then I can filter index on 2020. And you can see that all I've got there is 2020 data. And so that's just a nice, handy little feature, kind of a shortcut. Okay, so I've been singing the praises of the tidyverts with respect to the tidyverse verbs and how compatible everything is. And that is true. There are a few verbs that don't work as you might expect, and that is group by and summarize. Now, maybe this isn't a surprise to you, but when I first saw this, I was like, why can't I get rid of that index? But when I thought about it, it kind of made sense to me because by its nature, a Tsibble is a time indexed data frame, right? So getting rid of it would basically take away what makes a Tsibble a Tsibble. So if I'm for the ADHD skew, I'm going to group by item, summarize by quantity, and then I see what I get here is I have just the item, none of those demand group, none of the demand group data is there, but I still have my index. So if you wanted, let's say you wanted to summarize, you just wanted to get a summary for this SKU, you would just basically over here, you could, in this workflow, you could basically convert it to as Tsibble, and then nothing in the parentheses, and then you would get your standard group by summarized result. Okay, missing values. This is definitely a big deal for time series because it's a sequence as opposed to cross-sectional data where it doesn't have the same necessity of sequential data. So sometimes, and I say sometimes because this is my life, the way my company stores data, we don't have a row for a zero value. So I'm assuming it's saving space on our database or storage space, but if we didn't sell anything that month, there's just no record of it. Well, that's not good for time series forecasting. So we want to fill in the gaps. Of course, the tidyverts has a really great, easy function for this, and that is fill gaps, as aptly named. So you can fill the gaps either to the end of the series or to the beginning or both. So kind of a fully balanced panel there. So in this case, we want to specify to fill gaps to the end because not all items have history that starts at the same time. So I don't want to just write a bunch of zeros into any item that we didn't start selling until maybe, January 2019. However, we may have gaps at the end of this data if we've had zero demand in the past ones. And we do have a time series for which we've had zero demand for many months. So if you want to see if your Tsibble has gaps, you can call the has gaps function. And it produces a nice little table with a logical column that tells you if there are gaps. So we see that, I guess for 1, 2, 3, 4, 5 of these we don't have gaps, and then 3 of them we do. So then we know that we have to fill in some gaps. So we pass this Tsibble to fill gaps. So I've got my quantity variable here, and I specify 0L, so it's integer. Right? And then I say dot full to the end. So I pass that end special there. And we're going to take a look at this, the documentation of this function in just a second, because it can be a little bit, maybe a little confusing if you haven't used it before. So I want to make sure you guys have a good sense of how to use it for your particular situation if you're doing any forecasting. So then I run has gaps again, and you can see everything is false. So it worked as expected. So I'm going to go over here. So fill gaps. So you got your Tsibble, right? And then the dot full argument. So I chose n, so that pads NA, but of course it didn't pad NA because of other arguments I used to the same ending point, so the max index across units. So there's some good examples here that kind of illustrate this behavior. So you see here kind of what we were doing. There's a start. And then again, I kind of combined those two examples. You got 0L. And this is because I know that my gap mean is 0. You can also use a function to fill the gap. So that's appropriate in your case. You could use maybe a median, a mean. In this case, we have a sum. And what's also cool is that if you have a Tsibble where you have multiple quantity variables, you can just use commas and you have different things that you want them to be filled with. You can just use commas and separate them with what you want to fill them. So it's a very handy function to be aware of. Oh, by the way, I don't know if I should name but if you're wondering about these demand groups, I just realized that this is the first time we've seen a nice little summary of it all. These are basically distributors, big distributors that we sell to. We're a manufacturer, Mallinckrodt's a manufacturer. So that my coworker came up with these names to help him organize his data. So that's what that is about. Okay, so we're kind of moving on to step 3. We kind of done our data cleanup, and step 2, getting your data, figuring out what's going on with your data, is that would also be the place where if you had to do any data cleanup, like string trimming, with a tidyverse, that would be a good place to do that. In this case, I already did some of that ahead of time. I didn't want to, waste our time here running through a tidyverse cleanup of the data frame. So just a heads up about that. So plotting data is very important. If we can do, even if we're doing automatic forecasting, which is what my company is currently doing, and we will get into that shortly, or if you are specifying the model estimation yourself. So this allows you to see those patterns we talked about earlier. It also allows you to detect outliers. So I haven't touched on outliers yet. Now, you may be familiar with, there's an outlier definition where it's 1.5 greater than 1.5 times the interquartile range or less than negative 1.5 times the interquartile range. That's the technical definition. I'm just going to be honest with you. That's not always, you got to use your best judgment based on what you know of your data, what you know of maybe a customer demand or another event that would be kind of not something you would want to incorporate, you would want to predict in the future. So outlier detection and replacement is really important if we're doing automatic forecasting, because you are not controlling model specifications. So the old saying, garbage in, garbage out, right? When it comes to modeling, that definitely applies here. So actually my coworker and I, our hands-on part of our forecasting right now is basically doing outlier detection and replacement. Okay, so line plots. This is one of the simplest kind of plots, but it's just really useful in many scenarios. So got the Tsibble filtering just to our 8-9 item. That again, that's one of our acetaminophen items. And then I'm using the auto plot function, which you're probably familiar from ggplot 2. So auto plot basically just selects the best type of plot for your data. So this is ours figured out, it's time series data, right? So a line plot is generally a good choice. Cool thing is you actually don't even need to specify the variable. If you only have one quantity variable, the function is quote unquote smart enough to figure out what you're trying to plot. And I just added a label here so you can see what we're talking about. So I'm looking at this and I think I see a trend here. I see a lot of random variation that at first glance, you might say, oh, that's seasonality, but keep in mind, humans are pattern detecting machines, even when there aren't patterns. So always be wary of that when you approach your data. But it seems like starting around January, we're seeing kind of a downward shift here. So if I was going to specify a model myself, that would be something I wanted to keep in mind, that I might want to try a model with some trend in it. Okay, so seasonality. It was a good lesson for me because you can assume, when I was putting together this presentation, because you can assume that you have, that your data has certain characteristics. So we always kind of told ourselves a story at Mallinckrodt that, our acetaminophen products have a high seasonality, flu season, and then of course before back to school, which maybe you wouldn't have guessed, but obviously when kids are back in school, in-person school that is, there's more germs going around, right? So it makes sense when you think about it. But I was looking at all of my 100 or so SKUs, and I was like, none of these looks like, none of these looks like it's seasonality to me. So it's kind of a little humbling when you realize that maybe you didn't know as much about your data as you thought you did. So I asked my coworker, my boss, for some ideas, and they suggested, my boss suggested this family of SKUs. So ADHD, so you're probably thinking, okay, ADHD, why is that seasonal? And then you're probably also thinking, that's seasonality? Looks like a bunch of, kind of some randomish variations. Well, hear me out. You can see, down here we've got Januaries. You can see as we go towards mid-year, so most of our customers are Northern Hemisphere, so summer holidays are going to be in June, July, and August. Demand falls, and then as the school year starts, it picks back up. It tends to be higher on average in the winter months and the late fall, but we see this this falling off and then picking up for all of our years. Now, if you really want to see some great examples of seasonality, I recommend you go check out Forecasting Principles and Practice. I believe it's beer production, apparently in Australia, is highly seasonal, but that series is quite seasonal. This series, we're going to say there's some seasonality going on. So interestingly, so of course, 2020, we had the COVID pandemic really pick up here in the United States. We still see, even with remote learning, we're still seeing that dropping off and picking up going into the start of the school year. That's kind of interesting because maybe there were people going back to school. Maybe parents decided to continue filling the prescriptions that they had for kids. Obviously, it's not just children who take ADHD, but that's a good portion of the population for this product. So moral of all that commentary is be aware of the story behind your data, which you probably already knew that. So let's say I want to get a different view of this series and say, okay, am I imagining things? Is there actually some seasonal trend there? So you see it's the same, I'm doing this group by and summarize, it's easier to look at it all as one series here. And then the handy GG_season function. You can pass it, the variable, you don't need to. And you can see that we have all 4 years. Now we only have 1 month of January, so it's not going to be on here. This is a line plot. But we see that when you plot all the years against the months, you really see that pick up around August timeframe. It's a little bit more mixed in terms of the decline from the winter into the spring. You kind of see that, but definitely we can see what's going on here. I really like this seasonal plot. It's another way to look at your data, GG_subseries. Each of these blue lines represents the mean over the years in question. And then we see kind of the trend of the data each month over the years. So no surprise, June and July are low months. August, we kind of see things start to pick up, go to a relatively high level in Q4, a little bit more variation in the Q1. And again, this mean is brought down by, we had 0 demand, which is very unusual, in January. So another kind of plot that you might use, it's actually not just a plot, you can decompose time series into their various components. I'm just going to touch on this briefly here because, first of all, I don't really use decomposition a lot, so it's not more of a area of expertise for me, but I think it is good to be aware of this, especially if you need seasonally adjusted data. So if you work perhaps or you want to work for a government agency like the BLS where they want seasonally adjusted data, you can get components. But here, I just want to show you how it looks when you plot it. So we're kind of introducing a new function here. That is the model function. This model function is kind of a general workhorse for Fable. So in this parentheses, let's see, there's the end of the parentheses. I put the I just chose the STL decomposition. There's a lot of decompositions. You can read more about them in Dr. Hinman's book. This is a well-respected or widely used one. So you probably recognize this tilde syntax for a model. We have our variable, and then this is our trend special. So we want to break down to trend, and then seasonal components. I just specify robust equals true. You don't have to, but I thought it was a good idea. And then I'm extracting the components. And if I didn't auto plot from here, I could just have like a data frame of components, and that would be interesting to take a look at if I wanted to extract like the seasonal data of the trend component, that kind of a thing. But I'm just passing this to autoplot. And again, autoplot's a smart function, and we can see that it knows what to do with this. So we've got, this is the series. This is another acetaminophen skew 3,7. And the way that it has been decomposed is we definitely see the trend kind of decreasing around, what is that, July 2019. Okay, so there's some, looking at this, I would not say this is particularly seasonal data, but you give it a seasonal parameter, right? It's going to extract some kind of, it's going to almost force some kind of seasonality onto, some kind of seasonal component onto that. So we have some kind of seasonal component here. And then whatever isn't captured in this is our remainder. So just want to encourage you to look at, make sure you look at the different axes here, because they are different for different components. So just to kind of touch on the seasonal parameter, I set it to periodic, and that was basically forcing the seasonality to be the same across years. The default window is 21 for monthly data. You could, if you think trend is changing at a different rate, you might, play around with that. You really wanted to get a decomposition you were comfortable with. I just left it at the default for purposes of illustration. And unfortunately, we don't have time to look at the STL function in the fees package, but if you want more information, the function is pretty detailed, and it will give you a good idea of where to start. Okay, so now we're going to go into some simple forecasting methods. And these are intuitive methods that you may have used already. You can use them actually to forecast. Sometimes you get surprised how good a simple method can be. You can also use these, and what's more common is then to be used as benchmark for more complex forecasting methods. So kind of the idea is, hey, your model might not be great, but at least it's better than the benchmark method, right? If it's not better than the benchmark method and you can't get a better model, then maybe you should ask yourself, well, maybe I should just stick with a mean or a seasonal naive model. Well, why am I spending all this time if this is not a very forecastable time series? So as I mentioned, the mean forecast, notice they're all in caps. That seems to be convention for the Fable, different models. Then we got naive forecast. And naive is basically whatever the last data point was, that's the forecast. No, nothing changing. That's just what it is. Seasonal naive would be if you think you have seasonal data, so that's going to be whatever the last period was seasonally. So if we're having monthly data, you're forecasting February 2021, it would be whatever February 2020 was, and so on and so forth. The random walk is similar to naive, but you can add a drift parameter to account for trend. Let's take a look at some of these forecasts. I'm taking that 8-9 skew, that one we think has some kind of a trend. And again, there's our model function, and then within that, passes the mean function. So notice I'm using the window here. I don't have to use this window, but it seemed to me, given the fact that we have some kind of trend going on, that maybe I should only go back six periods. So that's why the size equals 6 parameter is there. Again, that's a judgment that I made. You might look at the data and decide you want to go back 12 periods, or not even just have it be the mean for the whole series. Then I forecasted H equals 1 year. So this is the first time we've seen the forecast function tonight, H being horizon. And then the cool thing about Fable is that you can just pass it like English language time statements, like 1 year. I could also say H equals 12. So either one will work. And then I auto plot. Now it's kind of cool because this auto plot again is smart enough to figure out. I just pass it the Tsibble again. And I do not need to filter it, which is pretty cool. And I specify level equals null. If I did not specify level equals null, I'd have confidence interval bands, 80% and 95% are the default. So that would be like a C, so it'd be basically a vector, C parentheses 80 comma 95 is the default. I could change that if I want 90% or another relevant interval. So I've got this blue line forecast here. I mean, it's not bad, I guess. You know, what a statement of confidence, right? But you know, I got a lot of random variation here. This seems reasonable. If I gave this forecast to, you know, someone in supply or my boss, he'd be like, well, okay, that's reasonable, I guess. So it's a reasonable benchmark. So now let's look at the naive forecast. So I just pass naive and then the quantity. And then I got this, I'm going to forecast 1 year. Okay, so the dangers of a naive model, this is a great illustration, when you have a lot of random variation. We happen to have sold 0 in January, and this is probably because we tend to pull demand because we want to meet our revenue goals. We pull demand into the year. So then sometimes our January is a little bit low. So we had 0 demand in January. So now, because that was the last demand value, I'm forecasting 0 for the entire year. Well, clearly that is not reasonable given all of this data. So again, be careful with a naive forecast. So related to the naive forecast is our seasonal naive forecast. And you can see that this looks more reasonable. It's basically copying right here, putting it into the future. Might be a little bit overfitting, and it's not, that's in the technical term, but in a sense in that, is it really reasonable to expect that it's going to follow the exact pattern we had in 2020? I mean, that wasn't the case going back, you know, 2019, 2018, but it's definitely better than forecasting 0. Okay, so now that we're talking about forecasting, I want to bring up the term fitted values. So every observation in a time series can be forecast using previous observations. These are called the fitted values. They are technically not true forecasts because the parameters you use to forecast them, especially if you're estimating parameters like linear regression, exponential smoothing, which we'll get into shortly, were estimated from all the observations. So it's kind of like you're almost cheating in a way. So in the forecasting literature, you'll often see this as y hat sub t given t minus 1, or just y hat sub t. So the other side of the coin of fitted values, is residuals. So this is what remains after you fit a model. So basically it's the residual E sub t is y sub t, so your demand minus your fitted value. Or I say demand, I'm so used to demand forecasting, to say your actual. Let's be more broad in our scope here. So the goal in time series modeling is to have the residuals not contain any info that is not accounted for in the model. So in other words, you would like them to be a white noise series. That's not always possible. Well, it's not always possible given the resources you have. Just speaking from personal experience and the time, obviously none of us have infinite time and modeling capability as well as access to data that might be, you know, relevant regressors. So if you want to obtain the fitted values and residuals, you're going to use the augment function. And if you've used the Broom package, you're probably familiar with the augment function. So taking our naive, I wanted to use naive for this example because it's really easy to see because the naive is simply the last value, right? So you can see right here, we've got our Tsibble, and then we have our quantity, and then we got our fitted values. We don't have, because of the nature of this model type, we don't have anything for January, the first observation in the series. But then you can see that our fitted value for February is basically January, March, it's February, and so on and so forth. And the residual, of course, is basically, or it is our actual minus our fitted. So we have some that are positive, some that are negative, and that's what you would expect, you know, in residuals. In fact, you wouldn't want them to be all positive or negative. That would not be a good thing, as we'll discuss shortly. So white noise. So white noise, we don't want, basically, we want a mean zero. White noise, mean zero, no autocorrelation, and ideally normally distributed around that mean zero, right? So there's various ways that you can test whether the residuals are white noise. You can kind of do an eyeball of it, and that usually is reasonably good. And that will plot the residuals across time. It'll plot an autocorrelation function, so you don't want autocorrelation in your residuals, right? And it'll plot a histogram, so you can kind of see, are they normally distributed, what's the mean, that kind of a thing. It's also advisable to do a portmanteau test for autocorrelation, such as Box-Pierce. The Leung box, I hope I pronounced that correctly. I do not speak Swedish. I believe the Leung box test is generally considered to be better. So we'll do that tonight. So the null hypothesis of the Leung box test is that the data is white noise. So you get a p-value less than 0.05, assuming you're going to that 95% confidence level. That implies the series is not white noise. So you reject your null hypothesis. Let's take a look at that naive model. So I modeled it, I passed it to the residuals, very, very simple code here. So I got to plot the residuals. I got, okay, so they kind of seem like they're around zero, right? Maybe. And I look at this histogram here, normal-ish, and you'll be hearing me say ish a lot lately, a lot tonight when it comes to residuals, because obviously it's not going to be, first of all, we don't have a large data set, so it's not going to be super close to the normal distribution, even if it is approaching that, just given the only 37 observations that we have. But it seems, the mean is zero here. And, we can kind of imagine a bell curve there. And then we go over to our autocorrelation function plot. And we have this 95% bands here. We've got, wow, that's definitely outside. That's outside. That's right there. That might be outside. I'm trying to hard to tell on the screen. So clearly it seems like this naive model, we can do better than this. There's information in the residuals that is not captured by this model and that theoretically could be captured. So now let's say I want to do the Leung box test. So I'm going to use that augment function again. Do that Tsibble with the residuals. And then I'm going to pass that to the features function of feast. So I put my series that I'm testing here, and that's .resid. Remember from the previous slide, that's what the residuals are called. And then we have just Leung box unquoted. Okay, so as no surprise here, we've got a fairly large statistic. We've got a very small p-value. So we reject the null hypothesis that these are white noise residuals. So this would be a good indication we should go back to the drawing board, kind of circle back, maybe just, step 3, step 4 kind of thing. Okay, so Janine, I think we had talked about maybe doing a break right about now. Does that sound good?
That sounds fine to me. Yeah, so
Okay.
5 minutes, 10 minutes, what do you want to do?
It's up to you guys. I don't care.
Why don't we come back in 10 minutes? So at 7:15, we'll start back up. And if you need to leave Zoom and come back, we'll let you back in at that point. We're happy to answer questions in the chat if you have any. right, I don't know if Laura is back from break, but it's about 7:15, so we can start back up whenever she's ready.
I am back.
All right, cool.
Okay, there's a screen share here. Okay. So exponential smoothing models, these are basically a family of models. There's like, I don't know how many off the top of my head, which are based on weighted averages of past observations. So the weight decays exponentially for less recent observations, so thus the name. There are a lot of different exponential smoothing models, and you can see those in chapter 8 of the book. I just want to give you an idea. Also, you might see the word state space model. With regard to exponential smoothing models, that is regarding the error, so like the distribution of the error. So just keep in mind that it's not something particularly different for your purposes of forecasting. So you can see there's lots of different kinds. Let me go to, I'll do this. So you might be looking at this and like, holy crap. Wow, there's like, there's all these different equations. So the point is, don't feel like you need to know all the equations to use these models. These are different kinds of trends, different kinds of seasonality. So the multiplicative error models, just you cannot use these if you have any zeros in the data. But as you can see, there's various equations that make it up. There's different ways to write exponential smoothing models. You can write it in 2 equations, or you can sometimes write in a single equation. So we're going to more focus on this one, the ANN one, and I'll show you what that means. So the ANN is called simple exponential smoothing, and that is suitable for data with no trend or seasonality, which is a surprising number of my SKUs. So that's SKU stands for stock keeping unit, or item basically. Unfortunately, because everybody wants to think that they've got this great structural model that they can use to predict, but that's not always the case. So this is a very colloquial kind of, not necessarily totally scientific way to think about it, but you can kind of think about it, if it helps you, as being between the extremes of the naive model. And as you saw, that's just the last observation. And then a mean model, which if you don't specify window, that will give equal weight to all observations. So the equation form, and this is not the 2 equations, which you can also have two equations to specify it. But the single equation form is you've got the forecasted value, and notice this big T. So that means this is after the end of our last observation. A T plus 1 given T is equal to alpha times the last observation plus 1 minus alpha times whatever you predicted the model predicts the last observation to be, given T minus 1. So you kind of back substitute, or think about it as a recursive process, right? That you kind of substitute back to the earlier observations and get that. It's a kind of interesting exercise to do that on your own if you'd like to play around with the math, but we're not gonna do that today. So alpha is the smoothing parameter. 0 is less than or equal to alpha, and it's less than or equal to 1. So the higher the value of alpha, the more weight is given to recent observations. So the sum of the weights, which the alphas, the 1 minus alphas, is approximately equal to 1. So when you think about that, kind of going back to the beginning of the set. So the parameters are estimated either by minimizing the sum of squared errors. So if you've done, OLS, you're probably familiar with that concept, or by maximizing the likelihood, so you may be familiar with likelihood estimation, that the data we observe arose from the specified model. So the default for the ETS function, which is the function we're going to use, is likelihood estimation. So that's how parameters are estimated, by maximizing the likelihood that we have that data. So ETS denotes, the E stands for the error type, the T stands for trend type, and then the S stands for seasonality. And that is the kind of the catch-all function for all your exponential smoothing models. So the cool thing about this function is that you can specify the parameters yourself. that you can specify a level of alpha if you want, beta, the smoothing parameter of the slope, gamma, depending on what kind of model you're using. Or you can just let the algorithm decide and basically do automatic forecasting. And you take a look at the function documentation, and I'll give you some more details about that. So this is important enough, I definitely want to take a look at this with you guys. The Tsibble package. So you can see we have the formula, optimization criterion, you have likelihood, right? That's the first one. There's other ones that you can see, mean squared error, sigma. I generally don't change this. You feel free to do that if you see a need to change it. So the information criteria used in selecting the model, we use the Kaike information criterion corrected, the corrected one, which accounts for the number of parameters that corrects from just the basic one. And that formula is given in the forecasting book. I'm not going to go over it here just for the sake of time. We also do Bayesian information criterion as well. Okay. So the specials that you can use are error, trend, and seasonality. So you have different methods for error, additive, multiplicative, as I alluded to earlier. You also have trend. So if you decide to use the trend special, you don't have to. Generally, you leave the alpha null. And then if you specify, for example, if you specify a trend or not, it will estimate the value of alpha. Here's the range. As you can see, it goes from very close to 0 to up to 1. Beta, so alpha is the smoothing parameter for the level. Beta is the smoothing parameter for the slope. So if beta equals 0, it won't change with time. So if beta equals 1, it's almost like a kind of an out of control process in my mind, no memory of past slopes. Generally, I have never seen on Stack Overflow or any kinds of examples, you might look around Google at different time series stuff. I've never seen people specify the alpha, betas, and phi, I guess I got it, phi. Generally, it's just, you don't want to restrict the model too much, just in my opinion, and it's better to let R do that for you. So the seasonal parameter, you got gamma, if you do have seasonality, and that's estimated. It's basically how much it's going to change over time. So there's a lot in this documentation. You may want to take a look before you start doing some models. And then there's some good references here to check out to see a little bit more about the theory behind it. Let's take a look at an example. So the easiest way to do it, and this is what we're currently doing in my company, is we let the algorithm select the best specification. As I mentioned before, it's the corrected Kaike information criterion. That is the default criterion. And in my mind, this has the added benefit of removing any bias a forecaster might have. So as I mentioned before, humans are pattern detecting machines. And it's so easy to think that, oh, there's definitely some seasonality there. It's like, no, it's just random variation, around some level. So it's also, I would recommend, especially as a beginner, if you haven't done this before, start out just letting it select the best specification for you. And you might want to decide to play around with it eventually and see how that changes. And I'll show you that with the Shiny app later on, but it's not a bad choice. In my company, we currently have about 1,000 time series that we need to forecast. And so it's just, well, it's sometimes not super feasible to do all of them, every month. Although my coworker, he really likes to be very hands-on with his data. So we might actually be moving to a Shiny app forecasting paradigm, but we'll see. So you do the modeling here. I decided to name the model. I can pass multiple models. If I had an ARIMA model, for instance, which unfortunately we do not have time to cover today, I could put that in there as well, and then have two models, but I'm just going to name it ETS for the ETS function. Then I'm going to report, and then I'm going to look at my residuals. Okay, this is the ADHD product, recall, and I'm forecasting at the SKU level, not at the SKU customer level. So this is very interesting. This is the series, if you remember, that I was like, I think there's some seasonality there. And maybe the algorithm is a little conservative, which, okay, I guess that makes sense if in terms of just throwing parameters into the model for no good reason. So we have our level, sigma squared, and then we have, this is what you might want to take note of. So you've got your AICC, 640. This number is not particularly relevant unless you're looking at, if you want to see how it changes for that data set. I will mention this here, there are very, you cannot always compare AICCs between models, between model types. If you difference the data, for instance, you can't compare between those kinds of models. So just be cautious in comparing the AICC. So now look at my residuals. Seems to be still some trend maybe in there. I don't know. That's definitely not normally distributed. And doesn't look like mean zero. So the interesting thing is there's no autocorrelation in the residuals based on what I'm seeing here. As you can see at 12, it's very close to 95%, but it doesn't look like it crosses the threshold from what I can see on the screen. So this would be only get the case because it's kind of close where I want to take a look at the Leung box test. So my p-value is greater than 0.05. So I'm not going to reject the null of white noise. So I could say, okay, maybe I was reading too much into the data. I'm just going to go with that. Sometimes you have to use a little bit of judgment. So I might test out a seasonal model just to see. So this is how you use one of the specials inside the ETS function. I'm going to take this SKU and I'm going to say, okay, the error and the trend can be anything, but I definitely want an additive seasonality. Report and then do the same kind of analysis again. So we have alpha, we have gamma. Oops, let me go back. We got alpha, we got gamma. Gamma is very small. Then we have our initial states level, and then we have for each of our months here, and no surprise, June and July, right, are very low. And then we have the fall months pretty high. The residuals, I mean, we got this outlier here. They look better to me just at a glance. This is closer to a normal distribution around mean zero. We definitely don't have anything going on here with autocorrelation. So this is kind of where it gets into the art of forecasting. I might decide that, no, you know what, I think I know better. I'm going to go with a seasonal model. And then what I would probably do is see how it performs over time. And maybe I decided, well, I don't know as much as I think I do. I think I'm just going to go with a simple exponential smoothing model. So yes, there is a lot of judgment involved, as with any, not just time series modeling, but as you're probably aware, any kind of modeling. So here's some more examples of how you can use the specials. So you can also put in more than one. You can put a vector in the, for example, a trend. So that SKU, the acetaminophen SKU, which we saw some trend there. Let's say I'm convinced that it's definitely a trended model. And I say, okay, either additive or additive damped. Additive damp basically damps the trend. You can kind of see the equation. You can see the equations in the book if you want to find out more about the math behind that. And I get my alpha, my beta, very small, so not a lot of weight on the alpha recent observations. And then we have initial states, CI AICC. Again, this is a different SKU, so not something I would compare. And I look at my residuals, right? Not terrible, maybe some stuff going on here as we go further along the series. Normal-ish distributed. Nothing across that dotted blue line. I do a Leung box test to see, and my p-value is 0.438. So I cannot reject the null of white noise for the residuals. So I might say, you know what, I'm okay with this model. I might try out a simple exponential smoothing, or I might just let it do an automatic forecasting. I probably might compare several models if I wanted to do that. And that is made easier with the Shiny app, you'll see. Okay, so white noise residuals, I've kind of been beating that drum for a while. They are important. But the ultimate test of how well a model does is how it performs on data it hasn't seen before. So you could theoretically have a model that isn't that great from a statistical perspective, but you know, for whatever reason, it forecasts really well. And then maybe you have to swallow your pride and say, hey, you know what? I'm just going to go with that model, even though it's not the greatest from a statistical perspective. So residuals, again, because you can have the overfitting problem, are not a great judge of accuracy. Now they're better than nothing for sure. And you'll see how I make use of that in the Shiny app. But just be cautious when it's kind of a starting point for diagnosing your model versus like an ending point, if that makes sense. So now the concept of training and test data is relevant to forecast accuracy. So the simplest way, and I would say fastest way in terms of computational time to test your model, is to withhold the last 20% of observations as a test data set. So these are not going to be used to estimate parameters. So they will be true, they will really be good to compare to our forecasts. So we can have actual unseen by the model values to compare. So as you see, that January 2021 is our last observation. We have 37 observations. So we're going to withhold July 2020 through January. So again, our old friend filter index comes in handy here. And again, the syntax, you probably are familiar with this dot syntax from Tidyverse. I guess base R uses it to a certain extent too. So I'm setting up a training data set. So I'm filtering it up to and including everything up to and including June 2020. Let's take a look at my training data. You can see I only have 240 rows now. So now I'm going to use this training data, and I am going to do some automatic forecasting. I'm going to model all the SKUs at once. I'm going to forecast 7 once, and then I am going to look at the accuracy. So this is really, I guess, intuitive syntax in my mind. This is kind of cool, is that you don't even need to do any filtering or anything here. R will be able to match up the relevant data from your full demand Tsibble, right, to the forecasted values by SKU and by month. So it's really, really useful feature. So you can see we get a table here with different models, and we have our different SKUs and demand groups, test data. This would be training for just doing residuals. And we have all these different variables. So MAFE, MACE, ACF1, we're going to cover that autocorrelation function. And we will talk about these now and what they mean for the forecast accuracy. So the default for the accuracy function is point accuracy measures. There are also interval and distribution measures. Full disclosure, I've not used those, so I really can't speak to the best ones to use and the best way to use it. But you can read more about that in the documentation of accuracy if you are interested. So in the forecasting context, the error, forecast error, is defined as E sub capital T plus H. So remember, T is the last value of the time series, equals the actual value minus the forecasted value. It's not the fitted value, it's the forecasted value, because we're talking about in the future here. H is our forecast horizon. So as you would guess by the name of error, we want that to be as close to 0 as possible. So the closer to 0, the better forecast. So the point accuracy measures include the ones that aren't percent based, which we'll get into shortly, mean error, ME, and that's just the mean of the errors. Mean absolute error, the mean of the absolute errors. You take the absolute of all those errors, and then you take the mean. And then we have root mean squared error. RMSE, which is the mean of the error squared, and take the square root of that. So if you have a forecast method that minimizes MAE, they'll get you forecasted median, but the forecast method that minimizes RMSE gives you forecasts of the mean. That's why we like RMSE. Generally, you want a mean forecast in terms of we think about our forecast distribution. Unfortunately, RMSE is not as intuitive. Okay, percentage point accuracy measures. So percent error, as you are probably familiar with this formula, it's basically 100 times, 80% is going to be 100 times whatever you're talking about over the denominator, right? In this case, it's an error, so we have our error over our demand in this case, or actual. And then the error, of course, is our y sub t minus y hat sub t. So you think of it as error over demand for a given time period. So the nice thing about percent errors is that it's easy to compare between data sets. They are unit independent. It won't be useful though in the accuracy function. There are zeros since division by zero is undefined. And the two mean percent errors that you're going to see in the accuracy function are MPE, that's just the mean of all the percent errors, and then mean absolute percent errors, that's the mean of the absolute of the percent errors. So this is probably my favorite forecast accuracy measure out of all the point accuracy measures. So that's MACE. Dr. Himen and his collaborators created that. I want to say it was probably about 15 years ago. If you Google MACE, maybe MACE forecasting, Rob Himen, you should be able to find the original article that was written back in like 2006 or something, if you're interested in learning more about it. So basically it is how accurate the forecasts are from a given method relative to a one step ahead naive forecast. Or if you have a seasonal method, it's seasonal naive. So the nice thing about this is it kind of gives you an idea of, are you beating a really dumb forecast, for lack of a better word? So a value less than 1, given that it's a ratio, indicates the model produces forecasts that are at least better than that. So you can always congratulate yourself that you're doing better than a naive method. And as you would expect, the lower the base, the better the forecast. So don't be intimidated if you don't like certain formulas by this. This is our scaled error. And we have, basically what we have here is, because this is assuming it's just a naive forecast, not seasonal naive, we've got the absolute of the difference between yt and minus yt minus 1. And that is because naive forecast is just basically last value is the future value. So we take all the absolute, sum of the absolute of that, t minus, and this is starts at t equals 2, goes up to t. And so then taking the mean of that, we have t minus times 1 over t minus 1, since we don't have the full t number of observations. And then we have the error for our method. So MACE is basically the mean of all the absolute of those errors. So let's kind of wrap this up and think about some things to consider when you consider how to judge your forecast. So RMSE is useful for comparing accuracy between models. So if you have the same data and you want to say, does my RMSE go up has it gone up or down? It's not particularly intuitive as a data point, because obviously if you have a high volume item, you're going to have a higher RMSE, even if the model is better than a lower volume item in general. So MACE is good because it shows how much better it performed relative to that benchmark. And it's also kind of scale independent. Also keep in mind, if you see the infinite value, any of those percent metrics, percentage point accuracy metrics, that means there's zeros in your data. And unfortunately, then you can't use it. So a more sophisticated method is cross-validation. Interestingly, the AICC, which we looked at before, is analogous to cross-validation. So that's why it's considered such a good, that's why the automatic forecasting algorithm uses it as, to pick a model, so to speak. But if you want to do cross-validation, it's a more sophisticated, but it is computationally intensive. But I mean, it takes a long time generally to do. So what you're going to do is you're going to stretch the Tsibble into multiple data sets of increasing size. And then you're going to estimate the models and forecasts. Then you'll compare those to the data set actual values that were withheld. So I'm going to take a look at this graphic so you can see this is really useful. I really like this graphic. So essentially what you're doing is you're stretching that data set. So if this is one step ahead, right? So we do this, then we estimate a model on this, one step ahead, estimate the same model, same parameters in this, right? You keep doing that until you get to the end of the data set. In this case, we're going up. The default is to go up by 1, increasing the set size each time. You could go up in multiples of 3 or something like that, or I'm sorry, by 3. Generally, 1 is reasonable. So what we did, I'm just going to do this for our 8-9 skew. I'm going to stretch the Tsibble, and then I set the initial size to be 6. That is, as I recall, don't quote me on this, but I believe I am accurate about this. You need at least 6 observations to estimate an exponential smoothing model. So then what I'm doing here is I'm estimating an exponential smoothing model for the stretched Tsibble. Okay, now what I should have done, and I was realizing this recently, but I haven't changed the PowerPoint. I should ideally specify a model, maybe a simple exponential smoothing model. So I make sure at least the same structure of the model goes through every one of those little mini data sets, so to speak. But I did it, but this will still be good for illustrative purposes. So I'm just going to forecast 1 ahead for each time, each of these tiny little data sets. I'm going to take a look at the accuracy. So the wording isn't particularly relevant. It does generate because you have out of sample data. Let me head over here. I'm going to do this. And then I'm going to do this a little bit. Hopefully it won't take too long. I filtered it to just 1 skew to kind of, well, it's still going. We'll give it a few more seconds here. See if there we go. Okay. And we have 0, so we have this problem still. So we got our MACE, we've got our RMSE, and we've got our mean error. Now, if we had, and I think for the sake of, see, 7:45, kind of coming up on time here. If you wanted to see the different models that were estimated, you could just stop it. You could cut out the rest of this code if you want to go back and take a look. It's kind of interesting to see that. Or you could just specify your own model here. That's what I would recommend. And then you could augment it, or just take a look at what kinds of or use a tidy function from the Broom package just to see what are the values of the alphas or the betas or the gammas, as you will. So it's kind of interesting to take a look at that. We'll say I really don't. I want to say one of the first Shiny apps I built for time series, I used this. It took so freaking long that I was like, no, this is not going to work. And so then I just did residual accuracy, which isn't the greatest, but it is a little bit more time cognizant. But yes, just be aware of this. This is a little bit more advanced, but I wanted you guys to be aware of it. So automatic forecasting, you've already kind of seen this. Just wanted to kind of emphasize how nice this is. And then I'm calling the tidy function here, right? If you wanted to see the exact model, this is a little trick I found out recently, that you could actually say, okay, you could mutate and then do another column where it was like format like ETS, and that would give you like ETS, ANN, or whatever. But this is good. You can see that we have all of these 8 models. They only have alpha and L. So that basically means they're all just simple exponential smoothing model was the model that was chosen for all of these. We see our level, we see our alpha. A lot of these, some of these alphas are a little bit bigger, some of them are really teeny tiny. And then we use this model object called a Mabel. Yeah, I did the tidy, then I'll give you a Tsibble, but the model object is called a Mabel. The forecast object is called a Fable. It's nice and tidy there, I guess. So then you see your mean. And then you see a distribution type variable, which is seasonally distributed, and then you have your standard deviation here. So that's your mean forecast. You can see it starts at the next month and goes forward. We're not going to look at all this, but it goes forward 1 year for each series. Okay, weighted MAPE. Wanted to touch on this because this is what my company uses, and I like it for if you end up working ever in a consumer packaged goods, retail manufacturing context. It's a really useful metric. So it's nice because it's easily scalable across many SKUs and time periods. The formula is you've got the sum of all of the forecast errors, whatever forecast horizon you're interested in, divided by, this is for like a given SKU's forecast, divided by some of the actuals. So it's kind of now very similar to some of those metrics we saw earlier. So this allows SKUs and time periods with more volume to have greater weight. So that's if you're interested in measuring your forecast accuracy across a business context where you want to give more weight to your cash cow SKUs, this is a good metric to see how you're doing. Maybe you don't care as much about your smaller SKUs and how good your forecast accuracy is. A very practical consideration is that it overcomes the problem of division by zero because you're highly likely to have zero for, you know, all SKUs across a given period or all periods for a given SKU. Okay, so a little Shiny app. This is I haven't published this to shinyapps.io. Let's hope this works well. Okay, so what I have is I have my SKU here. This is updates with whatever product group is available. And my trend type, my seasonality type. I only allow for additive errors, multiplicative errors, and sometimes give you weird models, just my unscientific personal experience. And then I have my residuals over here. So that's definitely not a normal distribution. So yeah, we have some stuff going on with residuals. Then you can see I have residual forecast accuracy. MACE, yeah, not surprising. I'm doing worse than a naive method. That's not good. So yeah, try some seasonality. So the MACE goes down. I will say again, when you put seasonality into data, you got to be careful that you might be subject to the overfitting problem. But I don't know. Let's take a look at the residuals, see what they look like. I still have that one outside the 95% confidence level. You know, I might go with this, say, okay, well, it's better at least on the MACE, even though the residuals don't look that great. It's hard to make a case for a trend. If I had cleansed the data here, I would probably, this is an outlier. I would probably maybe bring this down a little bit. Okay, so again, here's, I have a seasonality type. Could do none. And that's a reasonable forecast. It's not fancy, right? But it makes sense given what we've seen recently. Take a look at our residuals. Okay, not bad. I can also change start date here. So this is the kind of, if you were going to do interactive forecasting, I definitely recommend doing a Shiny app. So yeah, I might say the some seasonality. And there's always a possibility this maybe is a little bit overfitting. I don't know. Well, I mean, pretty not normal distribution, but close, something approximating it. So anyways, I hopefully, let's see, I'll just show you guys changed. So I can change the horizon that it considers. Say I'm going to go back to January 2019. Do that. That'll change what I get. Residuals will change too. So Okay. So hopefully that gives you kind of an idea of how you can forecast with exponential smoothing. I'll go to the question slide. There is so much with time series forecasting. I have just touched the surface, scratched the surface here. There's time series linear regression. We have hierarchical forecasting, various kinds of models, of course, ARIMA models. I thought I was gonna talk about ARIMA too, but not enough time. Let's see, what else? You got autoregressive neural networks, kind of unstable, but interesting, and dynamic regression. So all kinds of stuff that you can do. And, but hopefully this has inspired you to maybe go out and try some forecasting on your own if you haven't already. Thank you.
Oh, thanks so much, Laura. That was great. I learned a lot about time series. That was fantastic. Do any of the participants have questions for our speaker before we thank her for the evening? If you're getting a standing ovation, I think there's some hands clapping around the screen. Great. Well, I'm happy to stay on. I mean, we're scheduled till 8, so I'm happy to stay on and answer questions. But I would just invite you to join me in thanking Laura for her time and her expertise and all her great code. And really appreciate your contribution to Our Lady St. Louis and for helping us finish out our season really well. So thanks.
Great. I enjoyed talking to everybody. This was fun.
All right. So, you know, I can stick around. I'm not sure if Laura can stick around. Otherwise, we'll see you all at the next Our Ladies event. Keep an eye on our Twitter feed just in case we have something pop up in the summer. Otherwise, we usually go from September to about April each year. All right, hearing no questions, I think I'm just gonna call it and end the show now. So you can catch up with us on Meetup or Twitter if you want. Thanks again, Laura.
Thanks.